I'll tread, but I can't quite swim. Hide a little bit longer. Hide a little bit longer.
All right, guys, welcome to our lecture on Laws of Logarithms. We've talked about logarithms a couple of times already this semester. We've seen them in different contexts. We've talked about what they are. We've talked about how we can find them. And most importantly, we've talked about how they're related to exponential functions. So let's do a quick, super quick refresher. So recall, if we have a equals b to the x, then, well, what does that mean for log? So the whole point was that, remember that logarithms and exponential functions are inverses of each other. And then our big thing with inverses is that we're just swapping the input and the output. So remember, x was our input, right? We would input something for that exponent and then get out what b was raised to that exponent, right? So that was our output. And we were swapping those. So for logarithm, we had base to base. So we ended up with a base of b, right? Base was the same. And then our input was our old output, right? So that a became our input and x became our output, what it was equal to, the value of the function. So because of all this, right, this x is what we were raising b to get a. So we could think of logarithm, log base b of a, as being the same thing as saying what exponent do I raise b to get a. So that's what this is asking. What exponent, right? The question, log base b of a, should be equal to x, which is the exponent that we can raise b to get a. So let's look at a couple of examples of this. Again, we're still refreshing. This is kind of from last time. So if we were looking at log base 3 of 9, what do we raise b, which is 3 here, to get 9? So 3 raised to what equals 9? What exponent do I raise 3 to get 9? What's the answer? 2, right? 3 squared is equal to 9. So the answer overall is 2. All right, let's say we're looking at log base 2 of 8. Very similar, right? What do I raise 2 to get 8? What's the answer there? Again, it's a nice number, 3, right? 2 raised to the third power, 2 times 2 times 2 is equal to 8. All right, this is one of those tricky, hopefully you know your log rules, or not log rules, exponent rules question. All right, let's say I've got log 374. super big. We must be dealing with something super hard. I'm just kidding. What can I raise 374 to get 1? What can I raise anything to get 1? Well, the answer is 0, right? Remember, that's one of our sort of facts that for any real number, right, any real number greater than 0, if we raise b to the 0, we get 1. That's one of our facts. Okay, let's do a couple other ones that help us remember some of these older facts. So for example, let's say we're dealing with log base 7 and we want to know what we've got to raise 7 to get 1 over 49. So this one is a little bit tricky, but not terribly tricky. Just want to sort of refresh these rules in our mind. Not trick, but the rule that we want to use here is this one. So remember, b raised to the negative n is the same thing as taking the reciprocal of b to the n, right? That negative means that we want to take the reciprocal. So b to the negative n equals 1 over b to the n. If we look at this guy, we've got 1 over 49. Maybe you'll recall that 49 is 7 squared. So we know that this is 1 over 7 squared. So what is something else that this is equal to? Well, from this fact, we know that this is equal to 7 to the negative 2, right? If we have it flipped over, right, if we have the reciprocal, then it means that we can rewrite it as 7 to the negative 2, which means that we've raised 7 to the negative 2 to get this guy, and our output is negative 2. The last one I want to look at really quickly, just to get a little bit of a refresher for all these exponent rules. Let's say we've got log base 16 of 4. What can we raise 16 to get 4? Well, what is the relationship here? We know that 4, how is 4 related to 16? Well, we know that it's the square root of 16, right? That's an important thing to be able to recognize. How can I write this as something with an exponent? Might be something that we need to sort of dig out from the memory logs, but remember, we can write the square root of something as that thing raised to the 1/2. So that's one more fact that I want to kind of remind us of. So the square root of x is equal to x to the 1/2. And similarly, if we have the cube root of x, that's x to the 1/3, and so forth, right? So here, what's the exponent that we've raised that we've raised 16 to get 4? Well, we've raised 16 to the 1/2, so this is equal to 1/2. Great, okay, so that was a nice little review. Not super short, but I think all of those are very important for us to remember as we're moving into this next lesson. So let's start talking about the properties of logarithms. So we want our bases to be greater than 0. That's very important. We can't have a base that is less than 0 or negative. First one is one that we sort of covered just now. Log base b of 1 is going to be equal to what? We just talked about this question here, where if we have log base something of 1, we remember that that means that we've got b, that base raised to the 0 is the only thing that's going to give us 1. So we know that this here is always going to be 0 because of this rule. All right, another property that we have, we know that log base b of b. So what's that going to be? I'm going to get a little sheet of scrap paper here. So let's think about what log base b of b is, sort of thinking about the exponential form of this, right? So we're asking, what do I raise b to get b? B to the what gives itself? It's just 1, right? Right? Something raised to the 1 is itself. So that's easy. All right, so if I've got log base b of b to the x, what does this equal? So we can think about this in 2 ways. The first way that we can think about this is by doing the same thing that we did here. So log base b of b to the x. Let's think about this in terms of flopping to exponential form. So b to the what is equal to b to the x. Is it more clear now? B to the what equals b to the x? Well, this is just x, right? The other way that we can remember this, or something that is important to think about when thinking about this, is remember that we have this rule that when we compose inverses, remember the point is when we, and this is way back from very early in, I think module 2. Sorry. All right, so we have some input. We put it in, right? The function, we put it into the function takes it, spits it out, gives us the output. But then our inverse takes that output, right? That's what we're doing with composition, and it spits us right back out at the input. So if we put in x, we do the composition, and we get right back out to x. Both ways. It works the same way if we're going this way as well. So because of that, we know, and because we know that log base b is the inverse of b of x, then this is equal to x. And in the same way, b raised to the log base b of x is also equal to x. This is not something we're going to see very often, but I think it's important to sort of see the relationship here. But that's not to say that it's going to be on like a test or anything. Okay, so let's do a couple of examples with this, and I'm going to do this in this, do that in this side margin here. So let's say we have log base 3 of 3. Well, what is that going to be equal to? We can easily see it if we look at our rules here, or we can think about, what do I raise 3 to get 3? In order to get 3 back, when we raise it to something, it has to be 1, right? And that's our second rule. Okay. Log base 5 of 25. Well, of course, we know that 25 is 5 squared. Now looking at our rules over here, we can look at this third rule, and we see we've got this same structure and our x value is 2, and that means we're going to be equal to 2. Let's say we've got 2 raised to the log base 2 of 3. Well, let's look at our rules. If we look at this fourth one, we've got this same structure. We've got b is 2 here, x is 3. So that means that our answer is 3. And let's take that one step further. I want us to see that we can use this in sort of an algebraic way. So let's say, what would happen if I had 7 times 2 to the log base 2 of 3? Can I multiply 7 and 2? Is that what I should do first here? No, I cannot, right? Because remember, PEMDAS, right, please excuse my dear Aunt Sally, tells us that we have to do exponents before we can multiply. So this 2 needs to be raised to this exponent. It's an ugly exponent, but it needs to be raised to this exponent before we can do this multiplication. So we can't turn this into 14. We have to keep them separate. But the nice thing is that we know what this is equal to, right? We just did that up here. So we know that this is equal to 7 times, and again, math is all about replacing the stuff with more useful stuff. 7 times, this is not very useful, but 3 is pretty useful. So my full answer is just 21. All right. All of these can be applied to natural log. Here, properties. Natural log, again, is just short for log base e of x. So let's look at these guys. We can sort of use all of these rules that we just came up with in terms of natural log. So the first one, right, instead of log base b, we're using log base e for sure, so we can just write ln. We're just talking about ln. So same thing, right? If log base b, for whatever we're talking about, of 1 is 0, then ln is included in that. So ln of 1 should also be 0. All right, so our second rule was log base b of b. So what is our base here? Well, our base is, again, e. So the analog for that second rule would be ln of e is equal to 1. Similarly, we have ln of e to the x. We know that that should be equal to, right, if we have the base is the same, then we know that we're just equal to whatever that exponent is. And then, last but not least, we've got this rule. Here. So let's look at a couple of examples of those really quickly. Let's say we've got 5 times ln of e. So what is that equal to? Well, we want to look at this first. And we should know exactly what ln of e is equal to. 1, right? So So we've got 5 times 1. We can replace that ln of e. We've got to bring the 5 along. This is just equal to 5. Okay, this one's going to look a little bit crazy, but it's not as scary as it seems. This looks like some serious math. What rule does this look like? Well, we've got e to the ln of something, and we know that it's going to be equal to whatever's on the inside there. So what's on the inside here? What's pi? That's it. That's the answer. Last one. Let's say we've got 2 times ln of e to the 4th. What is ln of e to the 4th? Well, we can look at our third rule here. Ln of e to the something is equal to whatever it's raised to. So this guy, right, is equal to 4. So we've got 2, got to bring the 2 along for the ride, times 4, and the whole thing together is equal to 8. Okay, so product rule. This is sort of our first really cool thing that we've got going on with logarithms. So product rule is actually very cool. So product rule says that if I have log base b for some base of x times y on the inside of the logarithm, right? Remember, logarithm is a function. So just like we would say f of x, right, with the parentheses, right, f and then the parentheses f of x, we are going to say log base b of x times y. Log base b of x times y. So if we take the log of two things that are multiplied together, we can actually split it up into log base b of x plus log base b of y. This is due to sort of the way that exponent rules work. So the way I like to say it is that multiplication inside means, and that's a double arrow, right? Arrow going in both directions, means addition outside. And the reason I say it like this, I'll say it here so it's not permanently in our notes. This is not true. That's not true, right? Multiplication on the outside cannot become addition on the inside. It's multiplication on the inside is the same thing as addition on the outside, can become addition on the outside. So this ties in. Again, we have sort of the analog for natural log is equal to just ln of x plus ln of y. So this allows us to do a couple of things. One of the things we can do here is combine functions. So an example of combining might look like this. So we have log base 4 of a plus log base 4 of b plus log base 4 of c. So based on our rule here, we know that addition on the outside, which we have, if we have the same base, we have to have the same base. We have the same base here, it's all 4. This is equal to log base 4 of, and then since we're adding these all, we can turn it into multiplication on the inside. A times B times C. It's kind of like a funky rule. I really like this because it sort of turns the rules of algebra inside out, kind of, right? So I think this type of stuff is fun. We can also use this to expand. So, for example, if we've got something like log base 3 of maybe 5 times x times y, this is equal to, I'm going to write it on the next line. This is equal to log base 3 of 5, right, plus log base 3 of x plus log base 3 of y. We'll get more practice with this in just a minute. Okay, let me scoot up here. So, power rule. Power rule tells us that if we have log base b of x to some power, right? We have log base b of x to some exponent. Power rule tells us that we can take this exponent out front so that this would be equal to c times log base b of x. So the analog for natural log, of course, is just going to look like this, right? This c comes out front. We have c times ln of x. So this is very simple. It just means that if we have something like log base 2 of 5 cubed, this power just comes right out front. Easy as that. Let's say we've got log base 3 of the square root of 5. So how can we use the power rule here? Well, it doesn't even really look like we have a power. But is that true? Let's think back to that example we did earlier. The square root of something can be written as a power, right? Remember, the square root of x is equal to x to the 1/2. Cube root of x is equal to x to the 1/3. So here we have log base 3 of 5 to the 1/2. Now that we have a power, we can bring that out front. So we end up with 1/2 log base 3 of 5. Last one. So let's say we're looking at something like this. Power rule tells us that if we have this coefficient, it's the same thing as having, right, if we have some coefficient out front, it's the same thing as having that power up here. So we can sort of bring this guy in, right, it works both ways, as an exponent. And sometimes we'll need to do this, and I'll show you why that is right now. We can use these rules together. So, for example, let's say we have something like ln of a times b cubed. So we need to be careful about what we can do here, right? We obviously have an opportunity to use product rule, and we also have an opportunity to use power rule. Can we bring this 3 out front? We cannot. So remember, this 3 is a power of b only, right? If we were raising both a and b to the power of 3, we would have to have parentheses here, right? So this 3 is only being applied to this b. So we can't bring it out front because it's not an exponent for the whole thing here. So we've got to split these up before we can bring that 3 out. So let's split them up. Now, since this 3 is being applied to the whole input here, we can bring it to the outside, but it's not applied to that a. So let's look at one more. So let's say we've got this guy. So log base 3, we want to split up. So let's go ahead and split these guys up. We've got log base 3 of x plus log base 3 of y plus log base 3 of cube root of z Remember, from those rules we just looked at, we know that the cube root of z is the same thing as z raised to the 1/3, right? So this is equal to log base 3 of x plus log base 3 of y plus 1/3 log base 3 of z. We can use these two rules together to come up with another rule called quotient rule. Both of these rules together give us something called quotient rule. Okay, so quotient rule tells us that if we have log base b of a quotient, so x over y, something like this. This means that we can split this up into log base b of x minus log base b of y. The way I like to say this one, right before we said multiplication inside means addition outside, I don't want to say that division inside means subtraction outside, because there's a very specific order that we want to use. So I think it's important to think about it in this way. Denominator inside means that it's negative outside. So notice the y is in the denominator on the inside, and the y term is the one that's subtracted on the outside. So, and the super nice thing is that this spells dino. D-I-N-O. I don't know, maybe that helps, maybe it doesn't. If it doesn't, forget it. If it does, great. All right, guys, I just wanted to note here that I forgot to include the quotient rule for natural log. But remember, just like with all the other rules that we've looked at so far, it looks exactly the same, except instead of log base b, we have ln. So let's practice with this. So if I've got log base 3 of a minus log base 3 of b, what can we do with this? How can we combine it into one logarithm? Well, we've got to make sure we have the logarithm with the same base. We want to make sure we have the same base. This subtraction, right, this negative on the outside means that this b is going to be in the denominator. So we have a over b. What if I've got, ln, what if I've got ln of a minus ln of b plus ln of c minus ln of d? So this one is kind of tricky, right? We're subtracting. Does that mean that we divide by b times c? It doesn't, right? Because in order for c to be in the denominator, it needs to be negative on the outside, but it's positive. So this c is actually going to be on top. So we have a is positive. We're dividing by b. We're multiplying by c on top, and d is also in the denominator. So this is our answer. So let's try all of this together. So I'm going to draw sort of a divider because these are the examples specifically for quotient rule, and these are some other examples. So let's say we've got log base 2 of x squared divided by y times 7 cubed. Lots of stuff to split up, but it's going to be totally fine. We've got to split up using quotient and product rule first. So before we can use power rule when we're splitting. So we know that we've got log base 2 of x squared, right? That's the term that's on top. And then underneath, we've got minus y's down under there, y is underneath, and also z cubed is underneath. Now that we've got these all separated, right, now that each individual term is has the exponent applied to it, we can use power rule. So power rule tells us that this 2 comes out front, y is on its own already, so we're totally good there, and then this 3 comes out front as well. Let's say we've got 2 ln of a minus ln of b plus 1/2 ln of c, minus, this should be minus, plus 3 ln of d. Sorry, I double messed up on this one. So this is 1/2, so minus 1/2. Before we can combine using before we can combine using product or quotient rule, we have to make sure that they don't have these coefficients out front. A coefficient of -1 is okay, right? And then we can use quotient rule, but if we have a coefficient of 3 or 2 or 1/2 or whatever, that's not okay. We need them to have a coefficient of 1 or -1 before we can use product or quotient rule. So we have to bring all these guys inside. So ln of a squared minus ln of b minus ln of c to the 1/2 plus ln of d. All right, now that we've got a sort of clean slate, we can combine all of these guys. We know that a squared is positive. This is all equals. A squared is positive, so, or this term including a squared is positive, so that guy goes on top. B is negative, so that guy goes underneath. c to the 1/2 is negative, so that guy goes underneath as well. And remember that square root, or sorry, c to the 1/2 is equal to the square root of c. It's just another way of writing that. And then d is positive, so d goes on top. Gosh, I forgot the cubed here, right? This 3 comes inside, so we end up with d cubed, so d cubed goes on top. Okay, another example I would like to try out. This one's going to look pretty funky, but I want to make sure we can handle something like this. Log base 3 of the square root of x squared minus 1. So because it's all underneath this square root, we know that this is equal to log base 3. We can rewrite it as x squared minus 1 to the 1/2. We can't simplify further than this, right? We can't simplify this. We can't just take the square root of x squared and just take the square root of 1. Because they're being subtracted, we have to do this subtraction before we can square root, so we can't simplify this. So we have x squared minus 1 to the 1/2. Power rule says since that everything in here is raised to the 1/2, we can bring it out front. All right, we've got subtraction inside. Can we turn that into multiplication outside? No, we cannot. We cannot turn subtraction on the inside into multiplication outside or division outside. Remember, we have to be multiplying on the inside or dividing on the inside, and then that becomes addition or subtraction, respectively, on the outside. But because we're subtracting on the inside, we can't do any more simplification. So this is the answer. And then this is the last one I have for us in our notes. Let's say we've got 3 times ln of x minus 2. This is sort of a beefy problem. This is the final boss. Okay, so we've got 3 times ln of x minus 2 times ln of x plus 5 plus 1/4 ln of x minus 1. So again, we have to make sure we get these coefficients out of the way, so let's bring those inside first. So we've got ln of x cubed minus ln of, where does this 2 go? Does it go to just the x? No, we have to bring this 2 and apply it to everything that's on the inside here. So we have to apply the 2 to all of that. So x plus 5 squared plus 1/4, so that guy goes on the inside as well. And we have to apply it to everything inside there. And what does this 1/4 tell us? Well, this stuff in here is going to look like the 4th root of x minus 1. So when we put it all together, we can write it like that. But, all right, what is this equal to? So we've got ln. This x cubed term is positive, so it goes on top when we bring it on the inside, right? We are now condensing or combining using quotient and product rule. This second term is negative, so we know we're going to have to put that on the bottom. So we've got everything that's in there, x plus 5 squared underneath. And then this last one is positive, so we want to multiply on top. So we've got, remember we said that it's the fourth root, so we've got the fourth root of x minus 1 here. And this is the answer. Okay, there are a couple of lab manual problems that I would like for y'all to try. I will post the answers soon and I will let you know when I do that. Okay, thanks guys.